Welcome back to your second lecture within chemistry, CE chemistry. Tonight we're going to talk about a model of matter 1.3 and classifying matter 1.4. A hang glider soars far above the ground. How does this feat confirm that air is matter? Well, we need to go back and say, okay, what is matter? And matter is something that that has mass, remember, and that takes up space. So it confirms that it's matter because it is taking up space from the hang glider into the wings, and it is keeping aloft our hang glider. So when people explain things like this, we are using what is called the scientific models. And those scientific models actually explain what we observe in nature. Okay, so we've got two definitions that we need to get into our heads. One is molecule. Molecule is the smallest particle of a substance that has the properties of that substance. So in other words, if I have sugar, it's the smallest particle of sugar that still retains all the properties of sugar. Now, atoms make up molecules. So sugar is made up of carbon and hydrogen and oxygen. Those are atoms. So if I take a carbon, I would have an atom, or an hydrogen, I would have an atom, or an oxygen, I would have an atom. Once I put those together in a group that makes sugar, then I have a molecule. So now we're going to talk about John Dalton. He came up with a theory. He's credited with developing the first atomic theory containing ideas about the atom that we still use to get today. So we'll talk about each one. The first of his theory is that all matter is made up of tiny particles called atoms. The second is that substances called elements are made up of atoms that are all identical. The third is that substances called compounds are combinations of atoms of two or more elements. So, for instance, H2O is a compound, and it's a combination of hydrogen and oxygen. The fourth one is every molecule of a specific compound always contains the same number of atoms of each kind of element found in the compound. That's like H2O, no matter in the world, wherever I am, water is always H2O. Methane gas, wherever in the world I am, will still be CH4. Okay, so that's what it's talking about there. Okay, the fifth type is in chemical reactions, atoms are rearranged, separated, or combined, but never created or destroyed. So whatever I have before the reaction started, I will have after the reaction ends. They'll just be in different compounds. So for instance, I can start with methane gas and oxygen, but then I'll end up with CO2 and water. The same elements are there in the same amount on both sides. They've just rearranged and made different compounds. Okay, to give you an idea of what we're talking about, if we say oxygen, oxygen is actually a diatomic, and we show it here. And diatomics mean that they hang around in pairs. And you can see each of these are in pairs as you're looking in here. So when we write oxygen, we write O2. So it hangs around in pairs. We use graphical symbols such as circles and squares to represent different atoms. And we also use symbols like I just did here with the O2. This is carbon monoxide. You'll notice that the carbon there is black, and the oxygen is red because we had oxygen on the first one. And so I would write its symbol as CO, one for the carbon and one for the oxygen, to show that there's one of each running around here. But I can also show it graphically like it is shown in this picture. The far one here, you'll notice that we have one black with two reds. The reds again are oxygen and the black is carbon. So I would write CO2. We'll get to writing compounds later. Now, if it has two things together, there's several atoms that run around in pairs on the periodic table. And I had a teacher that I worked with that called it Braunhifkel. Let me write this down for you. Okay, Braunhifkel. He said it was his Russian girlfriend. Whatever, if it helps you to remember. Bromine, oxygen, nitrogen, bromine, oxygen, nitrogen, hydrogen, iodine, fluorine, and chlorine. These are elements that hang around in pairs. So whenever we see them alone, we would write Br2, O2, N2, H2, I2, F2, or Cl2. These are called diatomics. And it's a good thing to remember that they are diatomics. Okay, let's take a look at these photos again. We learned about diatomics on the last slide. Let's talk about some other things that we're going to be using as far as words. The first one that we need to talk about is called homoatomic molecules. Now when you talk about homo, that means same. So I'm looking for the atomic molecules that are the same. The ones that are the same are going to be oxygen. So this is a homoatomic molecule. The second type that we're going to be talking about is heteroatomic molecules. And that is hetero meaning different. That would be the other two, our carbon monoxide and our carbon dioxide. Those are heteroatomic because they're different. They're not the same throughout. And the last one, well, there's two others that we need to worry about as far as words. The first one is triatomic. Now diatomic was 2, triatomic is 3. And then the last one would be polyatomic. So if I have more than 3 that are attached to each other, I'm going to have polyatomic. Okay? Okay, so this is an example from your book where to use the terms diatomic, triatomic, polyatomic, homoatomic, and heteroatomic to classify. So let's look at the first one. The first one, we're over here, A. What do you see? How many molecules? Well, it's more than 3, right? So it's going to be polyatomic. And is it the same throughout or is it different throughout? It's different, so it's going to be heteroatomic. Okay, I want you to take a second and see if you can classify the others, and then I'll actually write the right answers for you. Okay, B is polyatomic and homoatomic. I hope you paused the video so you could try and guess. I'm going to put the rest up. So if you didn't, pause the video so you can see if you can do the rest. Okay, C is diatomic and homoatomic. And D is triatomic and heteroatomic. And E is diatomic and heteroatomic. So if we get those right, that takes us through the end of 1.3. We're going to go into 1.4, which is classifying matter. Matter, and we talked about what matter is. Remember, it is mass that takes up space. Can actually be broken down into 2 main groups. Mixtures, and we'll talk about those more in just a minute, and pure substances. Let's talk about pure substances first. In pure substances, we have a constant composition. So it's constant throughout. We also have a fixed set of properties. We also have that this cannot be separated anymore by physical means. Okay, let's look over here at mixtures. Mixtures are just that. They're mixes. So their composition is varied. They have different properties. They can be separated by physical means. And by physical means, we mean like chromatography. We can use magnets. We can use water. We can use all kinds of different things to separate. And they can be taken down to pure substances. One that a lot of scientists like to use is if you put a mixture of sand, salt, and iron together, iron filings. How would you separate it? You could get it back to your salt, sand, and iron filing, because you could use a magnet to pull out the iron. You could use water to rinse out the salt and then re-evaporate it and get the salt back, and then you would be left with the sand. You'd have to filter it off. So there's a lot of things that you can do to get back to your pure substances from mixtures. So that's important to know. Okay, there are two types of mixtures. The last one we were talking about with the sand, salt, and iron. If I had a mix and I took a sample, say right here, and I took another sample and it was right here, those two samples would be different. They'd have different amount of sand, different amount of salt, different amount of iron. Because of that, that type of mixture is what we call heterogeneous, meaning different throughout. It's still a mixture, but it is heterogeneous. Now, you'll also hear people talking about solutions. Solutions are a different type of mixture. Here we have, and this is just a picture from your book, here we have some sugar that's being dumped into some water. And when we stir it together, we actually get sugar and water floating around in there equally. Now, this type of solution, because it's the same throughout, if I let it stand, the sugar doesn't fall out. It's still in the water. This type of mixture is known as homogeneous because it's the same throughout. You probably have heard of homogenized milk, making it the same throughout. That's the same kind of thing. Homogenized being the same. Pure substances also break down into two different things. The first are elements, and those are just what we have up on the periodic table. They are the same thing. Now that can include our Braunhilfe, okay? So elements are just elements, just what's on the periodic table. The other side is compounds, and compounds are like water, like methane gas. They're a combination of elements, but they're always found the same way, okay? Okay, so this pulls it all together, and this is just a picture from your book. It's on page 11 or 13, depending on what edition you have. And this just basically breaks down. We started up here with matter, okay? And once we had matter, oh, it's not going to let me, there we go. Once we had matter, then we can break it down into pure substances or mixtures. And from the mixtures, we then get heterogeneous, meaning different throughout, or homogeneous, meaning the same throughout. In other words, it's all mixed in there. It's hard to get to see the different parts. In pure substances, we end up with elements. Remember, that's what's on the periodic table, like copper, and compounds, which is like sugar or water or methane gas or things like that. So we're going to need to be able to break matter down. And you need to be able to identify, do I have an element, a compound, a heterogeneous or homogeneous mixture? So that's really important. Okay, so here we have just drawn out again the grid so we can sort of see what's going on. Matter going to pure substances and mixtures, and then pure substances breaking down to elements and compounds, and mixtures breaking down into hetero and homogeneous. So we're going to try putting some things in there. So here we have something we need to choose, either element, compound, heterogeneous, or homogeneous. It is dirt with some bamboo shoots in it. What do you think? If you chose heterogeneous, you were right. Okay, so this is sugar. Where would sugar go? Homogeneous, heterogeneous, compound, or element? Well, sugar is the same, so it would be a compound. Okay, what about table salt? Where is table salt gonna go? Where do you think? Homogeneous, heterogeneous, compound, element? If you chose compound, that's right. Okay, how about a jug of milk? Where would milk go? Element, compound, heterogeneous, or homogeneous? Well, it's not an element. It's not a compound. It has lots of different things in it. Even though it has lots of different things in it, it's the same throughout, so it is homogeneous. Okay, here's some poppy seed dressing. So it has poppy seeds in it. So it is a mixture, right? So is it homogeneous, the same throughout, or is it heterogeneous? Well, you better have chosen heterogeneous, because the poppy seeds, you never know how many you're going to get. Okay, this is a copper pipe. Where is it going to go? It's homogeneous, heterogeneous, compound, or element. We're going to assume it's all copper, even though it has some patina on there. We'll talk about patina later. Actually is an element. Okay, we've got a silver spoon. What kind is it going to be? Homo, hetero, compound, or element? If you chose element, you did right. What about a bottle of Shout? What would you think about it? Where would it go? Is it an element? No. Compound? Heterogeneous? Homogeneous? Say homogeneous. Okay, here we go again. We've got this little molecule right here. It's not. Okay, we've got this little molecule right here. Just by the representation of what it looks like, is it going to be homogeneous, heterogeneous, a compound, or an element? What do you think? If you chose a compound, you were right. Okay, here we've got another thing. It's all sort of mixed in together here. That's a clue, so it's probably not a pure substance. It's got to be either heterogeneous or homogeneous mixture. Now, it's not separated in any way that can pull these apart from each other, so it's probably homogeneous. Okay, here we've got another one. Let me enlarge it just a little bit, maybe. Nope. Okay, it's actually got layers, so it can't be an element or a compound, but it's got to be a mixture. Is it the same throughout, or is it different throughout? This one is actually different throughout. Okay, we've got another little group right here. They're both the same. So could it be homogeneous, or is it it can be hetero because it's not different throughout. It's the same. Is it a compound, or is it an element? What do you think? This one is actually an element. Remember, some of the elements can hang around in groups of two. That Braunhifkel? Okay. Hopefully you've got the idea of how to classify now: element, compound, heterogeneous, homogeneous. I hope I've given you enough examples. And we'll see you in class.